Good evening, and welcome to The Sleepy Scientist. It's wonderful to have you here. Tonight we'll be looking at something that surrounds us, moves through us, powers stars, warms planets, and holds matter together, and yet remains surprisingly difficult to define. Energy. Just a little favour to ask before we begin. If you have a moment to spare, I'd really appreciate it if you took a look at our ebook over on the Sleepy Scientist website. It takes the ideas from these videos and gives them room on the page, unhurried, laid out with all the space they need to properly settle in the mind. The whole thing is narrated too, so you can read it, or simply listen. And at the close of each movement there's a short quiz waiting, a gentle way to see what stayed with you and to turn the ideas over once more before moving on. The QR code is up on screen, and there's a link in the description to thesleepyscientist.com whenever you're ready. Every reader who takes a look is the reason these videos keep appearing, and to anyone who takes the time to buy it, I don't think you quite understand how much that means. That's the only ask tonight, and thank you sincerely. Now, I'd love to know where in the world you're watching from tonight. Perhaps you're listening from a quiet bedroom, curled up on the sofa, travelling somewhere in the dark, or settling down after a long day. Wherever you are, I hope you're comfortable, relaxed, and ready to let your thoughts wander for a while. I'll try not to make energy sound too energetic, although the subject may not make that especially easy. So get comfortable, let the noise of the day begin to fade, and let's start with a deceptively simple question. What is energy? And how does quantum physics explain what it is really doing beneath the surface of reality? Energy is one of those words that feels completely familiar until someone asks what it actually means. We speak about energy when something moves, when something heats up, when a battery powers a device, when sunlight reaches the earth, or when the body turns food into motion and warmth. The word appears everywhere, yet it is not quite as simple as it first seems. Energy is not a substance hidden inside an object like water in a container. It does not slosh around invisibly, waiting to be released. Instead, energy is a measurable property of a physical system. It tells us something about the state that system is in, the changes it can undergo, and the ways it can interact with everything around it. A moving object has kinetic energy because of its motion. An object raised above the ground has gravitational potential energy because of its position within a gravitational field. A stretched spring has elastic energy because its shape has been changed. Warm matter has thermal energy associated with the motion and interactions of its particles. Fuels, foods, and batteries contain chemical energy because of the arrangements of electrons and atomic nuclei within their molecules. Light carries electromagnetic energy through space. These forms sound separate, but they're really different ways of describing the same conserved quantity under different conditions. Energy can pass from one system to another, and it can change its appearance without losing its identity. A falling stone offers a simple example. At the top of its fall, it has gravitational potential energy because of its height. As it drops, that potential energy decreases while its kinetic energy increases. When the stone hits the ground, its organized motion is transformed into other forms, including heat, sound, vibration, and the deformation of the stone and the surface beneath it. Nothing has vanished. The energy has simply become less obvious. This is the foundation of the conservation of energy. In an isolated system, the total amount of energy remains constant, even though it may move, spread out, or change form. The rule is so reliable that when experiments appear to show missing energy, physicists usually suspect that something unseen is carrying it away. The modern concept of energy developed gradually. In the 17th century, Gottfried Wilhelm Leibniz argued that motion involved conserved quantity related to mass and the square of speed. He called it living force. His idea was not identical to the modern definition of kinetic energy, but it moved physics toward the recognition that motion could be described by a preserved measurable quantity. Émilie du Châtelet played a major role in clarifying and defending this relationship. Through her studies of motion and her work on the ideas of Isaac Newton and Leibniz, she helped establish that the energy associated with motion depends on the square of an object's speed. This means that doubling speed does not merely double kinetic energy. It increases it by a factor of 4, which is one reason high-speed collisions can become unpleasant so quickly. During the 19th century, James Prescott Joule demonstrated the connection between mechanical work and heat. In his famous experiments, falling weights turned paddles inside water, and the motion caused the water's temperature to rise. Joule showed that mechanical energy and thermal energy were not unrelated substances. They were different forms of the same physical quantity. Hermann von Helmholtz developed the principle of energy conservation into a broad scientific law, applying it across mechanics, heat, electricity, magnetism, and biological processes. William Thomson, later known as Lord Kelvin, helped place energy and thermodynamics at the centre of modern physics. By the end of the 19th century, energy had become one of science's great organising ideas. It connected steam engines, electric currents, falling objects, heat, and light within one framework. Classical physics describes many of these exchanges extremely well. It can calculate the energy of a moving train, predict the behaviour of a pendulum, describe heat flowing through metal, and explain how electromagnetic waves carry energy through space. For the ordinary world, these theories remain extraordinarily successful. But at atomic scales, the picture changes. Atoms do not absorb and release energy in every possible amount. Electrons inside atoms occupy particular allowed energy states. Light can exchange energy in discrete quantities. Matter behaves not only like collections of particles, but also through wave functions, probabilities, and quantum fields. This does not mean there is a mysterious substance called quantum energy. Quantum physics does not introduce a new kind of energy floating beneath the ordinary forms. Instead, it explains the microscopic rules governing how energy is stored, transferred, and measured. Kinetic energy, chemical energy, heat, light, and mass all remain part of the same broader concept. Quantum theory reveals why microscopic systems possess the energy values they do, why some transitions are allowed while others are forbidden, and why matter can remain stable at all. The central mystery, then, is not whether energy exists. Its effects are visible everywhere. The deeper question is what energy becomes when nature is described through particles, waves, quantum states, and fields. For a long time, physicists assumed energy could vary smoothly and continuously. Then, a problem involving heat and light forced them to reconsider that assumption. The solution would introduce one of the smallest constants in nature and begin the quantum revolution. By the closing decades of the 19th century, physics seemed to be approaching something close to completion. Newtonian mechanics explained the motion of planets, projectiles, machines, and falling objects with remarkable precision. Thermodynamics connected heat, work, temperature, and energy. James Clerk Maxwell had united electricity, magnetism, and light within a single electromagnetic theory. To many physicists, the broad structure of nature appeared to be settling into place. There were certainly details left to calculate, but the deepest rules seemed largely known. The universe looked continuous, orderly, and reassuringly classical. Then physicists tried to understand the light emitted by hot objects. Any object with a temperature above absolute zero emits electromagnetic radiation. This is known as thermal radiation. The atoms, molecules, and charged particles within matter are constantly moving and interacting, and these microscopic processes produce electromagnetic emission. At everyday temperatures, Most of that radiation lies in the infrared region of the electromagnetic spectrum, beyond the range visible to human eyes. A warm hand, a cup of tea, and the walls of a room all glow in infrared light, although fortunately not brightly enough to make bedtime especially theatrical. As an object becomes hotter, it generally emits more total energy. The distribution of its radiation also changes. At relatively low temperatures, most of the energy appears at long infrared wavelengths. As the temperature rises, the strongest part of the emission shifts towards shorter wavelengths. A heated piece of metal first glows dull red. At higher temperatures it becomes orange, then yellow, and eventually approaches a bright white appearance as a wider range of visible wavelengths becomes intense. Stars follow the same general principle. Cooler stars tend to appear redder, while hotter stars appear bluer. To study this behavior precisely, physicists developed the concept of an ideal blackbody. Despite the name, a blackbody does not have to look black when it is hot. The term describes an ideal object that absorbs all electromagnetic radiation falling upon it without reflecting or transmitting any of it. Because it is a perfect absorber, it is also an ideal emitter. The spectrum of radiation it produces depends only on its temperature, not on the material from which it is made. A practical approximation can be created using a hollow container with a small opening. Radiation entering the hole reflects repeatedly inside and is very unlikely to escape. The opening therefore behaves almost like a perfect absorber. Radiation emerging through it closely resembles ideal blackbody radiation. Gustav Kirchhoff helped establish the theoretical foundations of this subject during the 19th century. He showed that the relationship between absorption and emission is universal under thermal equilibrium. He also recognized that an ideal blackbody spectrum should depend only on temperature and wavelength. Experiments gradually revealed several reliable patterns. Josef Stefan found that the total energy radiated by a hot object increases extremely rapidly with temperature. Ludwig Boltzmann later derived the relationship using thermodynamics. The Stefan-Boltzmann law states that the total power emitted per unit surface area is proportional to the fourth power of absolute temperature. This fourth power dependence is steep. If the absolute temperature of an ideal emitter doubles, the energy emitted from each unit of surface area increases by a factor of 16. Wilhelm Wien discovered another important relationship. Wien's displacement law describes how the wavelength of peak emission becomes shorter as temperature rises. In spoken form, the peak wavelength is inversely proportional to the absolute temperature. These results described major features of thermal radiation, but they did not provide a complete formula for the entire spectrum. Classical physicists attempted to derive that spectrum by imagining electromagnetic standing waves inside a cavity. Just as a plucked string can support particular patterns of vibration, an enclosed region can support many electromagnetic modes with different frequencies. According to classical statistical mechanics, energy should be shared among these available modes. The equipartition principle suggested that each mode should receive the same average amount of thermal energy. This approach worked reasonably well at long wavelengths. Lord Rayleigh developed the basic classical result, and James Jeans later refined its mathematical form. The result became known as the Rayleigh-Jeans law. Its failure appeared at short wavelengths. As wavelength decreased and frequency increased, the number of available electromagnetic modes grew rapidly. Classical theory assigned energy to every one of them. The predicted amount of radiation therefore rose without limit toward the ultraviolet end of the spectrum. According to the formula, a warm cavity should pour out enormous and ultimately infinite amounts of high-frequency radiation. Real objects did nothing of the sort. Measured blackbody spectra rose to a finite peak, and then fell sharply at shorter wavelengths. The classical prediction did not merely miss the exact height of the curve, it became completely wrong. This breakdown later became known as the ultraviolet catastrophe. The phrase sounds rather dramatic, but no laboratory oven exploded beneath a violet cloud. The catastrophe belonged to the theory, not to the equipment. The problem arose from the classical assumption that energy could be divided and exchanged continuously. If electromagnetic oscillators were allowed to take any amount of energy, then even the highest frequency modes could acquire small contributions. Since there were endlessly more modes at higher frequencies, their total predicted energy diverged. Energy conservation itself was not the difficulty. Physicists already understood that the total energy of an isolated system should remain constant. The deeper question was how that energy could be distributed among microscopic oscillators and electromagnetic modes. Classical physics assumed that every mode was continuously accessible. Nature appeared to disagree. The measured spectrum suggested that high-frequency modes were somehow restricted. They could not accept arbitrarily small portions of energy. Something in the microscopic rules prevented thermal energy from spreading smoothly across every possible frequency. The mismatch was quiet, technical, and deeply unsettling. Newtonian mechanics remained useful. Thermodynamics remained useful. Maxwell's equations remained magnificent. Yet when these successful theories were combined, they predicted radiation that did not exist. Max Planck approached the problem while searching for a formula that matched the experimental spectrum. In 1900, he introduced an assumption that he initially regarded with considerable caution. The oscillators in matter, he proposed, could not exchange energy in every possible amount. They could emit or absorb it only in finite portions related to frequency. Energy transfer, at its smallest scale, might not be continuous after all. Max Planck did not set out to begin a revolution. In 1900, he was trying to solve a stubborn mathematical problem involving the spectrum of light emitted by hot objects. The measurements were clear. The classical predictions were not. Planck's immediate goal was to find a formula that matched the observed black-body curve, not to dismantle the foundations of physics. He focused on the microscopic oscillators imagined to exist within the walls of a heated cavity. These oscillators could exchange energy with the electromagnetic radiation inside. Classical physics assumed that such exchanges could occur in any amount whatsoever. Energy was treated as a perfectly smooth continuum, divisible without limit. Planck introduced a different possibility. He proposed that the oscillators could emit or absorb energy only in particular finite amounts. The energy exchange would not be completely unrestricted. It would occur in discrete portions linked to the frequency of the radiation. Each such portion became known as a quantum. The word quantum simply means a definite amount. In this context, it refers to a finite unit involved in a particular physical process. It is useful to imagine energy being exchanged in steps rather than flowing through every possible value. But the picture should not be pushed too far. Energy is not always best imagined as a pile of identical little beads. Different systems have different allowed energies, and the size of a quantum depends on the frequency or structure involved. Planck expressed his idea through a simple relation. The energy of one quantum equals Planck's constant multiplied by the frequency of the radiation. This relation connected two things that classical physics had treated rather differently. Frequency describes how rapidly an electromagnetic wave oscillates. Energy describes the measurable capacity of a system to change or interact. Planck's equation said that the amount of energy exchanged in one quantum grows directly with frequency. Higher frequency radiation therefore involves larger individual energy transfers. Infrared radiation has a lower frequency than visible light, so an infrared quantum carries less energy than a visible light quantum. Ultraviolet radiation has a higher frequency than visible light, so an ultraviolet quantum carries more. X-rays and gamma rays have still higher frequencies and correspondingly greater energies per quantum. The constant linking energy and frequency is Planck's constant. Its value is approximately 6.626 times 10 to the power of minus 34 joule seconds. That number is extraordinarily small. Written in ordinary decimal form, it would require 33 zeros after the decimal point before the significant digits begin. Nature appears to have selected a very modest scale for the quantum of action. The tiny size of Planck's constant explains why quantization is not usually obvious in everyday life. At human scales, the energy involved in ordinary objects is enormous compared with a single quantum. Countless microscopic exchanges occur together, and the steps become far too small to notice individually. A dimmer switch, for example, appears to change the brightness of a lamp smoothly. A warm object seems to cool continuously. A rolling ball can appear to possess any speed within a broad range. Quantum physics has not failed in these situations. The underlying steps are simply so fine and so many particles are involved that the result looks continuous. The effect is similar to viewing a digital image from a comfortable distance. Up close, it consists of separate pixels. From farther away, the boundaries disappear into a smooth picture. The analogy is imperfect, but the general lesson is useful. Discreteness at a very small scale can produce continuity at a much larger one. Planck's proposal solved the black-body problem because it changed which electromagnetic modes could easily receive energy. In classical theory, every mode inside a cavity could absorb arbitrarily small amounts. Even an extremely high-frequency mode could take a tiny share of the available thermal energy. Since the number of possible modes increased rapidly toward high frequencies, classical calculations predicted an unlimited amount of short-wavelength radiation. Planck's quantization placed a cost on exciting each mode. Because the energy of one quantum increases with frequency, a high-frequency oscillator requires a relatively large minimum amount of energy before it can be excited. At a given temperature, many low-frequency modes can readily acquire the required quanta. High-frequency modes are much less likely to receive enough energy. This naturally suppresses the short wavelength end of the spectrum. The blackbody curve still rises as more modes become available, but it eventually reaches a peak and then falls because the energy quanta required at high frequencies become too large for thermal agitation to supply efficiently. The ultraviolet catastrophe disappears. Nothing needs to explode, and no infinite reservoir of ultraviolet radiation appears. The measured spectrum emerges from a restriction on how microscopic systems are allowed to exchange energy. Planck regarded this step cautiously. He did not immediately claim that electromagnetic radiation itself always travelled through space as localized packets. His model quantized the allowed energy values and exchanges of the oscillators in matter. Light could still be treated in many respects as the continuous electromagnetic wave described by James Clerk Maxwell. This distinction matters because Planck's original idea was narrower than the full quantum interpretation that followed. He had discovered that the interaction between matter and radiation required discrete energy units. He had not yet fully replaced the classical wave picture of light. In fact, Planck spent years trying to understand how his result could fit within established physics. The formula worked beautifully. Its meaning was more disturbing. A mathematical device introduced to explain the glow of a heated cavity suggested that energy at microscopic scales followed rules unlike anything in Newtonian mechanics or classical electromagnetism. The smooth classical world had acquired a hidden grain. Albert Einstein would take the next step. In 1905, he argued that the quantization should not be confined to oscillators inside matter. Under certain conditions, light itself behaved as though its energy were concentrated into localized quanta. Planck had divided energy exchange into finite portions. Einstein was about to ask whether the light arriving at matter came in those portions too. Albert Einstein's most famous equation would eventually connect mass and energy. But another of his discoveries began with something far more modest: light falling onto a piece of metal. In 1905, Einstein published an explanation of the photoelectric effect, a phenomenon in which electromagnetic radiation striking material causes electrons to be released from its surface. The effect had already been observed experimentally, but its behavior did not fit comfortably within the classical wave theory of light. According to classical electromagnetism, a brighter light wave carries more energy. It therefore seemed reasonable to expect that increasing the intensity of light should give individual electrons more energy. A sufficiently intense beam ought eventually to knock electrons free, even if its frequency were quite low. That is not what experiments showed. When light above a certain frequency struck a suitable metal, electrons were emitted almost immediately. Making the light brighter usually increased the number of electrons released, but it did not determine the maximum energy carried by each individual electron. That depended on frequency. Higher frequency light produced electrons with greater maximum kinetic energy. Lower frequency light produced less energetic electrons. Below a particular threshold frequency, no electrons were emitted at all, no matter how intense the light became. A very bright beam of low-frequency light could pour energy onto the surface without releasing a single electron. A much dimmer beam of sufficiently high-frequency light could produce electrons almost at once. This was difficult to explain if the energy of light was spread smoothly across a continuous wavefront. An electron should have been able to collect energy gradually from the incoming wave until it had enough to escape. If that were happening, weak light might produce a noticeable delay before emission. Instead, the response was effectively immediate. Einstein extended Max Planck's idea of quantization. Planck had proposed that matter exchanged electromagnetic energy in finite portions related to frequency. Einstein suggested that, under these conditions, the energy of light itself behaved as though it were concentrated into localized quanta. Each light quantum carried an energy determined by Planck's relation. The energy of one light quantum equals Planck's constant multiplied by the frequency of the light. An electron interacting with the radiation would absorb one complete quantum, rather than gradually collecting small fractions from the entire wave. The amount received therefore depended on frequency. Part of that energy was needed to free the electron from the material. The remainder became the electron's kinetic energy. Einstein expressed the relationship in a simple form. The maximum kinetic energy of an emitted electron equals the energy of the incoming photon minus the material's work function. The work function is the minimum energy required to remove an electron from the surface of a particular material. Different materials bind their surface electrons with different strengths, so they possess different work functions and different threshold frequencies. If the incoming quantum carries less energy than the work function, the electron cannot escape. Increasing the intensity merely supplies more low-energy quanta. It does not combine them into one larger unit for an individual electron under ordinary photoelectric conditions. It is a little like trying to enter a machine that accepts only coins of a certain minimum value. A bucket filled with smaller coins may contain plenty of total money, but if the machine examines them one at a time, none will open the gate. Nature in this case is surprisingly strict about exact change. When the frequency rises above the threshold, each quantum carries enough energy to overcome the work function. Any energy left over appears as motion of the emitted electron. Increasing brightness then increases the number of available quanta, and therefore tends to increase the number of electrons released. The distinction is essential. Intensity mainly controls how many photoelectric events occur. Frequency controls the energy available in each event. Robert Millikan tested Einstein's prediction through a series of careful experiments. Millikan initially regarded the light quantum idea with deep suspicion and hoped to examine it rigorously. His measurements nevertheless confirmed the linear relationship between the frequency of light and the maximum kinetic energy of emitted electrons. The experiments also produced an accurate value for Planck's constant. Millikan accepted that Einstein's equation worked, even while remaining uncomfortable with its physical interpretation. Scientific evidence can occasionally be rather inconsiderate toward personal preference. Einstein received the Nobel Prize in Physics for 1921, with the official recognition emphasizing his discovery of the law of the photoelectric effect rather than relativity. The word photon did not yet exist when Einstein proposed light quanta. The term was introduced by the American chemist Gilbert Lewis in 1926, although Lewis used it within a theory that differed from the modern meaning. The name remained, while the concept developed through quantum mechanics and quantum field theory. Modern physics describes a photon as a quantized excitation of the electromagnetic field. It is not simply a tiny classical ball of light travelling along a perfectly defined path. Photons produce particle-like, localized exchanges of energy and momentum, while electromagnetic phenomena also display interference, diffraction, and other wave-like behavior. A photon has zero rest mass, yet it carries both energy and momentum. Because it always travels through a vacuum at the speed of light, its energy is connected to its momentum rather than to a stationary mass. Photon momentum produces radiation pressure. Light reflecting from or being absorbed by a surface transfers momentum to that surface, creating a small force. The pressure is usually tiny, but across a sufficiently large, lightweight reflective sail, sunlight can provide continuous propulsion. Solar sails therefore move without fuel being expelled from an engine. They are pushed gently by the momentum of photons arriving from the sun. The energy carried by an individual photon varies enormously across the electromagnetic spectrum. Visible light photons typically carry roughly 1.5 to 3 electron volts. Red light lies near the lower end of this range, while violet light lies near the upper end. An electron volt is a convenient microscopic unit of energy. It is the energy gained by one electron when it moves through an electric potential difference of 1 volt. Ultraviolet photons carry more energy than visible photons and can trigger chemical reactions or damage biological molecules. X-ray photons commonly carry thousands of electron volts. Gamma-ray photons can reach millions, billions, or even larger numbers of electron volts, depending on their source. The difference between gentle infrared warmth and penetrating gamma radiation is not that one consists of energy while the other does not. Both are electromagnetic radiation. Their photons simply carry vastly different amounts of energy because their frequencies differ. Einstein's explanation showed that light exchanges energy in discrete events. Yet it immediately raised another question. If matter absorbs and emits only particular photon energies, then matter itself must possess particular differences between its internal energy states. The strange behavior of light was pointing inward, toward the hidden energy structure of the atom. The discovery that light transfers energy in discrete quanta immediately raised a deeper question. If atoms absorb and emit only particular photon energies, then the atoms themselves must contain a hidden structure of allowed energy values. At the beginning of the 20th century, the atom was still only partly understood. Ernest Rutherford's scattering experiments had revealed that most of an atom's mass and positive electric charge are concentrated inside an extremely small nucleus. Electrons occupied the much larger region around it, leaving most of the atom as apparently empty space. This nuclear model was a major advance, but it created a serious problem. If an electron were simply a small charged particle orbiting the nucleus like a planet around the sun, classical electrodynamics predicted that it should continuously emit electromagnetic radiation. A charged particle moving in a curved path is accelerating, and an accelerating charge should radiate energy. As the electron lost energy, its orbit would shrink. It would spiral rapidly inward and collapse into the positively charged nucleus. Classical calculation suggested that an atom built this way could survive for only a tiny fraction of a second. Ordinary matter was clearly more durable than that. Tables, trees, planets, and people do not collapse because their electrons suddenly become tired of orbiting. Something in the classical picture had to be missing. In 1913, the Danish physicist Niels Bohr proposed a model of the hydrogen atom that combined Ernest Rutherford's nucleus with Max Planck's quantization and Albert Einstein's light quanta. Bohr suggested that an electron could occupy only certain permitted orbits around the nucleus. Each orbit corresponded to a specific energy. While the electron remained in one of these stationary states, it did not continuously radiate energy, despite its apparent motion around the nucleus. This was a deliberate break from classical physics. Bohr did not derive the stability of these states from ordinary electromagnetic theory. He introduced it as a new quantum rule. The electron could not simply drift through every possible distance from the nucleus, or possess any arbitrary energy. Only particular states were allowed. For hydrogen, the lowest allowed state is called the ground state. It has an energy of approximately minus 13.6 electron volts, relative to a free electron infinitely far from the proton. The negative value indicates that the electron is bound to the nucleus. Energy must be supplied to remove it completely. Higher allowed states have greater energies and are less tightly bound. As the energy rises, the permitted levels become increasingly close together until the electron can escape the atom entirely. The spaces between these energy levels are not physical shelves inside the atom. They represent forbidden energy values. An electron bound within an isolated hydrogen atom cannot normally settle at an energy halfway between two permitted stationary states. This is atomic energy quantization made visible. An electron can move from a lower energy state to a higher one by absorbing a photon, but the photon must carry the correct amount of energy. Its energy must match the difference between the two atomic levels. Similarly, when an electron moves from a higher energy state to a lower one, the atom can emit a photon carrying away the lost energy. The transition rule can be stated simply. The energy of the emitted or absorbed photon equals the difference between the initial and final atomic energy levels. If the gap between two levels is large, the photon involved has a high frequency and a short wavelength. If the gap is smaller, the photon has a lower frequency and a longer wavelength. The atom does not usually absorb just any passing photon. A photon whose energy does not correspond to an allowed transition may pass by without being absorbed. The interaction depends on both the energy difference and additional quantum selection rules. These discrete transitions explain the line spectra produced by atoms. When hydrogen gas is heated or electrically excited, its electrons can move into higher energy states. As they return to lower states, they emit photons at particular wavelengths. When the emitted light is separated with a prism or diffraction grating, it does not form a perfectly continuous rainbow. It appears as a collection of distinct bright lines. Each line corresponds to a particular difference between two allowed energy levels. Long before Bohr's model, Johann Balmer had found a mathematical relationship describing several visible lines in the hydrogen spectrum. His formula successfully organized the wavelengths, but did not explain why nature produced them. Johannes Rydberg later developed a broader formula that described entire families of hydrogen spectral lines. Again, the pattern was clear even though its physical origin remained mysterious. Bohr's quantist atom provided the explanation. The Balmer and Rydberg formulas worked because the electron's energy was restricted to particular values. The observed wavelengths reflected transitions between those values. Different chemical elements contain different numbers of protons and electrons. Their electrons interact with the nucleus and with one another, creating distinctive arrangements of allowed energy states. Each element therefore produces its own characteristic pattern of emission and absorption lines. These patterns act like atomic fingerprints. Spectroscopy uses them to identify substances by examining the wavelengths of light they emit or absorb. In a laboratory, an unknown gas can be recognized from its spectral lines. The same principle works across enormous distances. When starlight passes through the cooler gases in a star's outer atmosphere, atoms absorb selected wavelengths. These missing wavelengths appear as dark lines in the spectrum. By comparing them with laboratory measurements, astronomers can determine which elements are present. Hydrogen, helium, sodium, calcium, iron, and many other elements have been identified in stars this way. Spectroscopy also reveals the composition of nebulae, the thin atmospheres of planets, and galaxies located millions or billions of light years away. Much of what is known about the chemical universe comes from reading the energy differences inside atoms. Bohr's model was remarkably successful for hydrogen, and for hydrogen-like ions containing only one electron. It reproduced the main spectral pattern and correctly connected atomic stability with quantist energy. But it was not the final theory. The model struggled with atoms containing several interacting electrons. It could not fully explain the strengths and fine details of spectral lines, and its picture of electrons travelling along definite circular paths was eventually abandoned. Electrons in modern quantum mechanics are not miniature planets following precise orbits around the nucleus. Their states are described by wave functions. These wave functions determine probability distributions, angular momentum, energy, and other measurable properties. Atomic orbitals are therefore not literal tracks. They are quantum states with characteristic spatial patterns and specific allowed energies. Bohr had correctly recognized the essential fact that atomic energy is quantized. His planetary image was a temporary bridge between classical intuition and a more unfamiliar description. To understand why the allowed energies exist, physicists needed a theory in which waves, particles, probability and energy were all connected. That theory would arrive through the work of Louis de Broglie, Erwin Schrödinger, Werner Heisenberg, and Max Born. The fixed energy levels of the atom would no longer be imposed as mysterious rules. They would emerge naturally from the mathematics of the quantum state. Niels Bohr had shown that atoms possess particular allowed energies, but his model still treated electrons as though they followed special orbits around the nucleus. The rules worked, especially for hydrogen, yet they did not explain why those energies were allowed in the first place. A deeper idea began with the French physicist Louis de Broglie. Light had already revealed a strange dual character. It could spread and interfere like a wave, yet it could also exchange energy and momentum in localized quanta. De Broglie wondered whether matter might display the same kind of duality. In 1924, he proposed that particles such as electrons should also have a wavelength. The relationship can be stated in spoken form. The wavelength associated with a particle equals Planck's constant divided by the particle's momentum. A particle with greater momentum has a shorter wavelength. A particle with smaller momentum has a longer one. For ordinary objects, the wavelength is so tiny that its effects are impossible to notice. A moving football has a de Broglie wavelength vastly smaller than an atomic nucleus. For an electron, however, the wavelength can be comparable to the dimensions of an atom, making wave behavior impossible to ignore. This idea offered a clue to atomic energy levels. A wave confined within a limited region cannot take just any shape. A string fixed at both ends, for example, supports only particular standing wave patterns. Each allowed pattern contains a whole number of half wavelengths between the endpoints. Other patterns cancel themselves or fail to fit the boundary conditions. An electron bound to an atomic nucleus is not literally a vibrating string, but the analogy captures something important. The allowed quantum states are restricted by the requirement that the wave-like description remain mathematically consistent. Only particular patterns are possible, and each pattern is associated with a particular energy. Erwin Schrödinger developed this idea into a general wave equation in 1926. The Schrödinger equation describes how the quantum state of a physical system changes through time. It plays a role in quantum mechanics, somewhat like Newton's laws in classical mechanics, although the object it evolves is not an ordinary trajectory. It evolves the wave function. A wave function is a mathematical object containing the information needed to calculate the probabilities of possible measurement outcomes. It may depend on position, time, and other variables associated with the system. It should not be imagined too literally as a thin cloud of physical material spreading through space. In some simple cases, it behaves mathematically like a wave, producing interference and standing patterns, but it is not an ordinary water wave, sound wave, or electromagnetic wave. Its meaning became clearer through the work of Max Born. Born proposed that the wave function itself should be interpreted through probability. More precisely, the squared magnitude of the wave function determines the probability distribution for possible measurement results. For a particle described in position space, regions where the squared magnitude is larger are regions where a position measurement is more likely to find the particle. Regions where it is zero correspond to outcomes that will not be observed. This probability is not merely a description of researchers being careless or uninformed. Quantum theory uses the wave function to predict a range of possible outcomes, even when the state has been prepared as precisely as the theory allows. The Schrödinger equation also explains why bound systems possess discrete energies. When the equation is solved for an electron confined by the electric attraction of an atomic nucleus, only certain stable solutions appear. These are known as stationary states, and each is associated with a definite energy. The same principle applies to many other bound systems. A particle trapped inside a small region, a molecule that can vibrate, or a quantum oscillator can possess a series of allowed energy states determined by the system's physical structure. The energies do not need to be inserted by hand in the way they were in Bohr's original model. They emerge from the equation and the boundary conditions. The mathematical quantity representing total energy is called the Hamiltonian. In many non-relativistic systems, the Hamiltonian includes the kinetic energy associated with motion and the potential energy associated with position and interactions. Together, these terms describe the total energy available within the model. The central relation can be expressed without symbols. When a quantum state has a definite energy, applying the Hamiltonian returns that same state multiplied by its energy value. A state satisfying this relationship is called an energy eigenstate. The corresponding allowed value is called an energy eigenvalue. The language may sound unusually formal, but the idea is straightforward. The Hamiltonian tests the state for energy. If the state has one definite energy, it comes back unchanged apart from being multiplied by that value. For such a state, an ideal measurement of energy always produces the same result. The state can still evolve with time, but its spatial probability distribution remains unchanged. Its time dependence appears as a changing mathematical phase. This phase matters when different states are combined, even though it does not by itself alter the probability distribution of a single stationary state. A quantum system does not always have one definite energy. It can exist in a superposition of several energy eigenstates. In that case, the wave function contains multiple allowed energy components at once. An energy measurement can produce any of the corresponding values, with probabilities determined by the contribution of each component. Before the measurement, the system is not necessarily hiding one ordinary classical energy that simply has not yet been uncovered. The quantum state itself may not assign a single definite value. This is different from an everyday object whose exact energy is unknown because no one has measured its speed carefully enough. In the quantum case, the spread of possible outcomes can be part of the physical state described by the theory. After an energy measurement produces a particular result, the system is left in a state associated with that measured energy, according to the standard measurement framework of quantum mechanics. These ideas connect energy with probability in a way classical physics never required. Standing waves remain a useful guide. A resonant cavity supports particular electromagnetic modes. A musical instrument supports selected notes. A bound quantum system supports selected states. Yet the quantum wave function goes further because it determines probabilities for measurements rather than representing only a familiar mechanical vibration. The energy of a quantum state is therefore not merely an amount carried by a tiny object. It is connected to the structure of the wave function, the Hamiltonian governing the system, and the possible outcomes revealed by measurement. A state with one definite energy evolves through time in a very particular way. A state that changes more visibly may require a combination of different energies. That connection between energy and time leads toward another unusual feature of quantum physics. Uncertainty is not always a flaw in observation. Sometimes it is built directly into the state itself. Werner Heisenberg's uncertainty principle is often introduced as though it were merely a warning about clumsy measurement. The usual picture suggests that a particle has perfectly definite properties. but the act of observing it disturbs those properties and prevents us from finding out what they were. That is not the full idea. Quantum uncertainty is not simply the result of imperfect instruments. It is built into the structure of quantum states themselves. Even when a system is prepared with great care, certain pairs of physical quantities cannot both possess arbitrarily precise values at the same time. The most familiar example involves position and momentum. A quantum state that is sharply localized in position must contain a broad range of momentum components. A state with a very precise momentum must be spread widely across position. This does not happen because the laboratory equipment is poor. It follows from the mathematical relationship between wave functions in position space and momentum space. Werner Heisenberg formulated the uncertainty principle in 1927, while quantum mechanics was still taking shape. The deeper lesson was that nature could not always be described as a collection of objects carrying perfectly definite classical properties before measurement. Energy and time are also connected through an uncertainty relationship, but the comparison must be handled carefully. Position and momentum are represented in standard quantum mechanics as observables. Each has a corresponding mathematical operator, and their uncertainty relation arises from the fact that those operators do not commute. Time is usually treated differently. In ordinary quantum mechanics, time acts as a parameter that labels the evolution of a state. It is not generally represented by a universal time operator in exactly the same way as position, momentum, or energy. For that reason, energy-time uncertainty is not simply another identical copy of position-momentum uncertainty. It refers to several related limits involving how quickly states change, how long unstable states survive, and how sharply energy can be defined over finite durations. A state with one perfectly definite energy is called an energy eigenstate. Its evolution through time is especially simple. The state acquires a changing phase, but its measurable probability distribution remains stationary. Nothing in its observable structure develops rapidly. The state may continue to evolve mathematically, yet its energy remains sharply defined. A state that changes noticeably over a short period generally cannot consist of only one exact energy. It must be built from a superposition of several energy components. Those components evolve at different rates. As their relative phases change, the combined state changes in a measurable way. This creates a fundamental link between the spread of energies in a state and the timescale over which the state can evolve into something distinguishably different. The relationship can be expressed in broad spoken form. The more rapidly a quantum state changes, the greater the spread of energy values generally required to describe it. One of the clearest examples appears in excited atoms. An electron in an excited atomic state may eventually move to a lower energy state and emit a photon. Some excited states persist for a relatively long time, others decay very quickly. If an excited state had an exactly defined energy and survived forever, the emitted radiation would have one perfectly precise frequency. Its spectral line would be infinitely narrow. Real excited states usually have finite lifetimes. Because they exist for only a limited duration, their energies are not infinitely sharp. The photons they emit therefore occupy a small range of frequencies rather than one exact value. This produces what is known as natural line width. A long-lived excited state has a narrowly defined energy and produces a narrow spectral line. A short-lived state has a greater energy uncertainty and produces a broader line. The general relationship can be stated as follows. The uncertainty in energy multiplied by the characteristic lifetime of the state is limited by a quantity related to Planck's constant. This does not mean that the atom's energy is wildly unpredictable. The broadening may be very small, and highly precise spectroscopy can measure it. The principle simply places a natural limit on how sharply the energy of a short-lived state can be defined. the same idea appears in unstable particles. Some particles survive for many seconds, while others exist for only tiny fractions of a second before decaying. Very short-lived particles are observed as broad resonances in collision experiments because their masses and energies are less sharply defined. Since mass and rest energy are connected, uncertainty in the energy of an unstable state can also appear as uncertainty in its measured mass. This is a genuine physical effect, not a failure of experimental skill. Energy-time uncertainty is sometimes explained through a more dramatic claim. It is often said that quantum mechanics allows energy to be borrowed from nowhere, provided it is returned quickly enough. This is misleading. Quantum physics does not issue temporary permission slips for violating energy conservation. In a closed system whose Hamiltonian does not explicitly change with time, total energy remains conserved. The uncertainty relation does not say that a system may briefly possess any amount of extra measurable energy. It says that states existing over limited times or changing rapidly may not have perfectly sharp energy values. That distinction matters. A short-lived state can have a spread of possible measured energies without total energy conservation being abandoned. The range belongs to the quantum description of the state, not to an actual bookkeeping error in nature. Virtual particles are often drawn into the same misunderstanding. In quantum field theory, calculations of particle interactions can be organized using perturbation theory. Feynman diagrams provide a visual way to represent the mathematical terms involved. The internal lines in these diagrams are often described as virtual particles. They are not ordinary particles directly detected in instruments. They are components of the calculation used to determine the probability of measurable processes. Virtual particles do not need to satisfy the same energy and momentum relation as real, freely propagating particles. But this does not mean they borrow energy from the vacuum or briefly violate conservation laws. At every interaction point in a Feynman diagram, energy and momentum are conserved. The internal mathematical quantities may not correspond to observable particles, but the full physical process still obeys the relevant conservation rules. The popular borrowing story survives because it is brief and memorable. Unfortunately, it is also the sort of explanation that becomes less accurate each time it is repeated. A better foundation comes from symmetry. Energy conservation in both classical and quantum physics is deeply connected to time translation symmetry. This means that the fundamental laws governing an isolated system remain the same as time passes. If the rules of an experiment do not change from one moment to another, then a conserved quantity associated with that symmetry emerges. That quantity is energy. In quantum mechanics, the Hamiltonian represents energy and also generates the time evolution of the state. The connection is not accidental. Energy is woven directly into the way quantum states change through time. Uncertainty does not weaken that relationship. It reveals that a state may contain a range of energy components, especially when it evolves rapidly or exists only briefly. A sharply defined energy brings a steady phase-like evolution. Rapid visible change requires several energies working together. Time and energy are therefore linked, but not because energy momentarily slips outside the rules. Their connection comes from the structure of quantum states, the finite duration of physical processes, and the symmetries that govern how nature evolves. Quantum mechanics is often associated with probability, uncertainty, and outcomes that cannot be predicted with complete certainty. Energy conservation, by contrast, sounds rigid and exact. At first, those ideas may seem difficult to reconcile. Yet quantum physics does not abandon the conservation of energy. It preserves it at a deeper level. A quantum measurement may produce one result from a range of possible outcomes, but this does not mean energy has appeared or disappeared without explanation. Probability governs which allowed result is observed. Conservation governs how the total energy of a closed system is distributed and transformed. The distinction is important. A system can have an uncertain energy before measurement, meaning that several energy values are possible. But the probabilities associated with those values evolve according to precise rules. When the system interacts with something else, energy can move between the two parts while the total energy of the combined system remains conserved. The strongest explanation of why this happens comes from symmetry. In the early 20th century, the German mathematician Emmy Noether discovered one of the deepest connections in theoretical physics. Noether's theorem shows that every continuous symmetry of the laws of nature is associated with a conserved quantity. A symmetry in this context does not simply mean that something looks balanced or visually pleasing. It means that a transformation can be made without changing the fundamental physical laws. Rotational symmetry means that the laws remain the same when an isolated experiment is turned to face a different direction. This symmetry is connected to the conservation of angular momentum. Translational symmetry in space means that the same experiment should follow the same laws whether it is performed here across the room or far away in another equivalent location. This is connected to the conservation of linear momentum. Energy conservation arises from symmetry in time. Time translation symmetry means that the fundamental laws governing an isolated physical system do not depend on the moment at which the experiment is performed. If the conditions are truly the same, nature does not use one set of rules on Monday and another on Thursday. A pendulum released today should follow the same physical laws as an identical pendulum released tomorrow. An atom prepared in a particular state should behave according to the same quantum rules regardless of the date printed on the laboratory calendar. When the laws remain unchanged under a shift in time, Noether's theorem identifies a conserved quantity. That quantity is energy. This makes energy conservation more than a pattern noticed in many experiments. It connects energy directly to the uniformity of time within the physical laws. In quantum mechanics, that connection appears through the Hamiltonian. The Hamiltonian is the mathematical operator representing the total energy of a system. Depending on the problem, it may include kinetic energy, potential energy, electromagnetic interactions, spin interactions, or other contributions. The Hamiltonian also generates the time evolution of the quantum state. This relationship can be stated simply. The way a quantum state changes through time is determined by the Hamiltonian that represents the system's energy. Energy is therefore not merely one property among many. It is built into the rule describing how the state develops from one moment to the next. When the Hamiltonian of an isolated system does not explicitly change with time, the expected total energy remains constant. The state may evolve, interfere, spread, or become entangled, but its total energy distribution does not begin drifting for no physical reason. This remains true even when measurement outcomes are probabilistic. Suppose a quantum state is a superposition of several energy eigenstates. An energy measurement may produce one of several possible values. The theory gives a probability for each result. The fact that the outcome is uncertain does not imply a failure of conservation. It means that the state does not assign one definite energy before measurement. Across repeated measurements of identically prepared systems, the same probability distribution appears. If the system evolves under a time-independent Hamiltonian, the probabilities associated with the different energies remain fixed. Individual outcomes may vary, while the structure governing them remains exact. Energy exchange becomes clearer when two quantum systems interact. An atom and the electromagnetic field can be considered as parts of one larger system. An excited atom may move to a lower energy state and emit a photon. The atom loses energy. The electromagnetic field gains precisely the corresponding amount. The transition rule remains straightforward. The energy carried by the emitted photon equals the difference between the atom's initial and final energy states. From the viewpoint of the atom alone, energy has left. From the viewpoint of the photon alone, energy has arrived. For the combined atom and field, the total remains unchanged. The reverse process also occurs. An atom can absorb a photon whose energy matches an allowed transition, moving into a higher energy state. The field loses energy while the atom gains it. Energy conservation does not require every part of a system to keep the same energy. It requires the total accounting to balance. The same principle governs particle collisions. In a collision experiment, particles enter an interaction region carrying energy and momentum. Afterward, the outgoing particles may differ from those that entered. Their directions may change, and entirely new particles may be produced if enough energy is available. Yet the total energy and total momentum before the collision must match the total afterward. Kinetic energy can become rest energy. Rest energy can become kinetic energy. Internal excitation can become radiation. One kind of particle can disappear while others are created. The forms change, but the totals remain constrained. Particle accelerators rely on this principle. When particles collide at extremely high speeds, their kinetic energy can be converted into the rest energy of heavier particles. Those unstable particles may then decay into lighter products, whose combined energy and momentum preserve the original totals. Conservation laws allow physicists to reconstruct invisible processes. If measured particles leave with less energy or momentum than expected, researchers look for additional particles that may have escaped detection. This logic helped reveal the neutrino. In beta decay, the observed electron appeared to carry only part of the available energy. Wolfgang Pauli proposed that an unseen neutral particle carried away the missing share. The energy had not vanished. Something difficult to detect had taken it elsewhere. Quantum physics has repeatedly rewarded this kind of careful bookkeeping. There is, however, a subtle complication when gravity and the large-scale universe are included. In general relativity, energy and momentum are conserved locally. Matter and radiation still exchange energy consistently within small regions of space-time. But defining one total energy for the entire expanding universe is more difficult. A changing curve space-time may not possess the same global time translation symmetry as an isolated system in ordinary quantum mechanics. Cosmological redshift provides an example. As space expands, the wavelength of travelling light increases, and the measured energy of each photon decreases. Asking where that energy has gone does not always have a simple global answer, because the expanding universe does not behave like a static box with an ordinary conserved total energy. This does not mean that energy conservation fails casually, or that local processes become unreliable. It means the global concept depends on the symmetries of space-time itself. Within atoms, molecules, laboratories, particle collisions, and ordinary interactions, conservation remains extraordinarily precise. That precision allows enormous collections of quantum particles to form stable matter. Electrons exchange energy with electromagnetic fields. Atoms bind into molecules. Particles scatter, decay, and reorganize while remaining constrained by the same underlying rules. Probability determines which possibilities nature realizes. Symmetry determines which quantities cannot simply disappear. And through time translation symmetry, energy remains one of the deepest threads connecting every quantum change. The stability of matter begins with a restriction. Electrons cannot arrange themselves around atomic nuclei in any way they please. Their possible states are controlled by quantum mechanics, and those rules determine the size of atoms, the structure of the periodic table, the formation of chemical bonds, and much of the behavior of the material world. An atom remains stable because its electrons occupy allowed quantum states with particular energies. The lowest available states are filled first, while higher energy states become occupied only when the lower ones are unavailable or when energy is supplied from outside. This arrangement is shaped by the Pauli exclusion principle. Wolfgang Pauli introduced the principle in 1925. It states that no two identical fermions can occupy exactly the same quantum state within the same system. Electrons are fermions. They possess a quantum property called spin, and each electron has one of two possible spin orientations when measured along a chosen direction. Because of spin and the exclusion principle, an atomic orbital can accommodate no more than two electrons, and those electrons must have opposite spin states. The word orbital does not describe a circular path. An orbital is a quantum state defined by a wave function. It has a characteristic energy, spatial distribution, angular momentum, and shape. As additional electrons are added to an atom, they fill orbitals in organized shells and subshells. The precise ordering depends on both the attraction to the positively charged nucleus and the repulsion between electrons. The lowest shell can hold only a small number of electrons. Higher shells provide more available states, arranged into subshells with different angular properties. This layered structure explains the repeating patterns of the periodic table. Elements in the same column often have similar chemical properties because they possess similar arrangements of electrons in their outermost occupied states. These outer electrons, often called valence electrons, are the ones most directly involved in chemical reactions. Helium and neon are unusually unreactive because their outer electron shells are filled. Sodium readily loses an outer electron. Chlorine readily gains one. Carbon can share electrons in several directions, allowing it to form an extraordinary variety of molecules. The periodic table is therefore not merely a convenient list of elements. It is a map of quantum energy states repeating in a structured pattern. Chemical bonding follows the same basic logic. Atoms form bonds when a combined arrangement of nuclei and electrons has a lower total energy than the separated atoms. The system moves toward a more stable configuration, and energy is usually released as the bond forms. In an ionic bond, one atom transfers one or more electrons to another. The resulting positive and negative ions attract through the electromagnetic force. Sodium chloride provides the familiar example. Sodium tends to lose one outer electron, while chlorine tends to gain one. The ions then arrange themselves into a crystal structure, whose total energy is lower than that of the separated neutral atoms. In a covalent bond, atoms share electrons. The shared wave function can extend across more than one nucleus, producing a state with lower energy than the separated arrangement. The bond in a hydrogen molecule forms when the electron states of two hydrogen atoms combine. One arrangement concentrates more electron probability between the nuclei and lowers the total energy. Another arrangement raises it and acts as an anti-bonding state. Metallic bonding involves electrons that are not confined to individual atoms. Many outer electrons become spread through the material, occupying collective quantum states across the metal. This helps explain electrical conductivity, thermal conductivity, and the ability of metals to deform without their atomic structure immediately falling apart. The distinctions between ionic, covalent, and metallic bonding are useful, although real materials often contain mixtures of these behaviors. In every case, the central principle is the same. The electrons and nuclei settle into quantum states that minimize the total energy while obeying the exclusion principle and the laws of electromagnetism. Molecules possess several kinds of quantized energy. Their electrons occupy distinct electronic states. The nuclei can vibrate relative to one another only in allowed vibrational states. Entire molecules can also rotate with quantized rotational energies. These energy scales are different. Electronic transitions generally involve the largest changes and often interact with visible or ultraviolet light. Vibrational transitions commonly interact with infrared radiation. Rotational transitions usually involve microwave or far infrared radiation. Because each molecule has particular mass, shape, and bonding structure, it produces a characteristic collection of absorption and emission lines. Spectroscopy can therefore identify molecules in laboratories, planetary atmospheres, interstellar clouds, and distant galaxies. The energy levels act as signatures written into light. Typical chemical bonds involve energies of a few electron volts. Breaking a strong bond may require several electron volts for each molecule involved. Nuclear processes occur on a much larger scale. Changes within atomic nuclei commonly involve millions of electron volts. This difference helps explain why nuclear reactions can release vastly more energy per atom than chemical reactions. Burning fuel rearranges electrons and chemical bonds. Nuclear fission and fusion rearrange protons and neutrons within nuclei. The amount of matter involved may be small, but the energy scale of each nuclear event is far greater. Quantum mechanics also allows processes that would be impossible in a strictly classical world. Quantum tunneling occurs when a wave function extends into and sometimes through an energy barrier that a classical particle does not have enough energy to cross. A classical ball rolling toward a hill either climbs over it or rolls back. A quantum particle has a probability of being detected on the far side even when its measured energy is lower than the barrier height. This does not mean the particle secretly gains extra energy. Its total energy remains conserved. The effect arises because the quantum state is not confined to the classically allowed region. Tunneling plays an important role in radioactive alpha decay. An alpha particle can escape from a nucleus by tunneling through the nuclear and electric barrier surrounding it. The same phenomenon appears in semiconductor devices, where electrons cross thin barriers inside diodes and transistors. A scanning tunneling microscope uses the extreme sensitivity of tunneling probability to distance. When a sharp conducting tip is brought very close to a surface, electrons tunnel across the narrow gap. Tiny changes in separation produce measurable changes in current, allowing individual atoms to be mapped. Tunneling also contributes to some chemical reactions, especially those involving very light particles such as hydrogen nuclei. It can allow reactions to proceed even when classical thermal motion would appear insufficient. The solidity of matter also depends on these quantum rules. When a hand presses against a table, the atoms do not behave like rigid miniature balls touching one another. The electron clouds interact electromagnetically, and the Pauli exclusion principle resists attempts to force identical electrons into already occupied states. The resulting resistance feels solid. Ordinary matter holds its shape because of electromagnetic forces, quantized electron states, and exclusion. Remove those rules, and atoms would not maintain their familiar size or structure. When enormous numbers of atoms come together, their individual energy levels begin to interact and split into closely spaced collections. These collective energy structures determine whether a solid conducts electricity, blocks it, emits light, stores heat, or becomes superconducting. The quantum rules that organize individual atoms therefore continue outward, shaping the behavior of entire materials. When a single atom is isolated, its electrons occupy distinct quantum states with particular energies. Bring two atoms close together, and those states begin to interact. Bring together billions upon billions of atoms in a solid, and the individual energy levels become so numerous and so closely spaced that they form broad regions known as energy bands. These bands are not physical layers stacked inside the material. They are ranges of allowed electron energies created by the collective quantum behavior of the entire solid. The Pauli exclusion principle is central to this structure. Identical electrons cannot all collapse into the same lowest energy state. Instead, they fill the many available quantum states in an organized way. As more atoms join the solid, each atomic energy level splits into a large number of slightly different levels. In a macroscopic piece of material, the number of levels is so vast that they appear almost continuous. Yet gaps can remain between them where no allowed electron states exist. Two of the most important regions are called the valence band and the conduction band. The valence band contains the highest range of electron states that are normally occupied at low temperature. Electrons in this band are often involved in holding the atoms of the solid together. The conduction band lies at higher energy. Electrons in this band are more free to move through the material and can carry electric current. The region separating them is called the band gap. The size of this gap, together with the way the available states are filled, helps determine whether a material behaves as a conductor, an insulator, or a semiconductor. In a conductor such as copper, electrons have access to unoccupied states at energies very close to those they already possess. The highest occupied band may be only partly filled, or two bands may overlap. This gives electrons room to respond when an electric field is applied. They can shift into nearby available states and develop a small net motion through the material. In an insulator, the valence band is filled and separated from the conduction band by a relatively large energy gap. Ordinary thermal energy or a modest electric field is usually not enough to lift electrons across it. The electrons remain bound within occupied states, and very little current flows. A semiconductor lies between these extremes. Its band gap is small enough that thermal energy, light, or carefully introduced impurities can promote some electrons into the conduction band. Silicon, one of the most widely used semiconductor materials, has a band gap of roughly 1.1 electron volts at room temperature. This is large enough for pure silicon to resist current more than a metal, but small enough for its electrical behavior to be deliberately controlled. The distribution of electrons among the available states is described by Fermi-Dirac statistics, developed through the work of Enrico Fermi and Paul Dirac. Electrons are fermions, so they obey the Pauli exclusion principle. Fermi-Dirac statistics gives the probability that an available energy state will be occupied at a particular temperature. At absolute zero, electrons fill the lowest available states up to a characteristic boundary called the Fermi energy. States below this energy are occupied, while those above it are empty within the idealized picture. At higher temperatures, the boundary becomes less sharp. Some electrons gain thermal energy and move into higher states, leaving vacancies below. In conductors, the Fermi energy lies within an allowed band, so nearby empty states are readily available. In many insulators and semiconductors, it lies within a band gap. When an electric field is applied, it exerts a force on charged particles. Electrons already move rapidly in many directions because of their quantum and thermal motion, but without an applied field, their movements average out. The electric field slightly changes the distribution of their momentum. A small net drift develops, producing electric current. The drift speed itself is often surprisingly slow, even though the electrical signal and the field through the circuit propagate much more rapidly. Electrons do not need to race individually from a power station into a lamp. The material already contains mobile charge carriers which respond collectively. Pure silicon can conduct weakly, but its behavior becomes far more useful when small amounts of other elements are added. This process is called doping. Adding an element such as phosphorus, which has one more valence electron than silicon, introduces electrons that can enter the conduction band relatively easily. This creates negative-type semiconductor material, usually shortened in speech to N-type material. Adding an element such as boron, which has one fewer valence electron, creates vacancies called holes in the valence band. These holes behave like mobile positive charge carriers. The result is positive-type or p-type semiconductor material. A hole is not a separate fundamental particle. It is the absence of an electron in a nearly filled band, but its motion through the material can be treated as though a positive charge is moving. Bring p-type and n-type materials together and a junction forms. Charge carriers diffuse across the boundary, creating an internal electric field and an energy barrier. This structure becomes the foundation of the semiconductor diode, which allows current to flow much more easily in one direction than the other. Transistors use related junctions and electric fields to control current. A small voltage at one part of the device can regulate a much larger current elsewhere. Billions of these microscopic switches can be placed onto a single computer processor. Their operation depends not on tiny mechanical gates, but on quantum energy bands, charge carriers, and carefully shaped electric potentials. Light-emitting diodes also rely on band structure. When an electron in the conduction band combines with a hole in the valence band, it can lose energy. In suitable semiconductor materials, that energy is released as a photon. The photon energy is closely related to the size of the band gap. A larger gap produces higher energy light with a shorter wavelength. A smaller gap produces lower energy light with a longer wavelength. By selecting and engineering different semiconductor materials, manufacturers can create light-emitting diodes that produce infrared, red, green, blue, and other colours. Photovoltaic cells perform the reverse conversion. When a photon with sufficient energy is absorbed by a semiconductor, it can promote an electron from the valence band into the conduction band. This leaves behind a hole and creates a mobile electron-hole pair. An internal electric field separates the charges, allowing them to travel through an external circuit and deliver electrical energy. A solar cell therefore converts electromagnetic energy into electrical energy through quantum transitions between bands. Solids can also display more dramatic collective quantum behavior. In 1911, Heikki Kamerlingh Onnes discovered that the electrical resistance of mercury vanished when it was cooled below a critical temperature. The phenomenon became known as superconductivity. The later theory developed by John Bardeen, Leon Cooper, and John Robert Schrieffer explained conventional superconductivity through the formation of Cooper pairs. Electrons normally repel one another electrically. Inside certain materials at sufficiently low temperatures, interactions with the crystal lattice can produce an effective attraction, allowing electrons to pair. These Cooper pairs behave collectively in a coherent quantum state. They can move through the material without the ordinary scattering processes that produce electrical resistance. Superconductivity is not simply perfect classical conductivity. It is a macroscopic quantum phase of matter, with effects including magnetic flux quantization and the expulsion of magnetic fields through the Meissner effect. The behavior of solids therefore emerges from enormous numbers of quantum particles sharing and competing for energy states. Band gaps determine whether electrons can move. Fermi-Dirac statistics determines how states are occupied. Electric fields reshape the distribution of charge carriers. Doping changes which states are easily available. From computer chips and solar cells to light-emitting diodes and superconducting magnets, modern technology depends on the controlled movement of energy through these quantum structures. The same many-particle systems also store and transfer thermal energy. Their electrons, atoms, and collective vibrations share energy statistically, linking the quantum behavior of solids with the familiar experience of heat. Heat feels continuous in everyday life. A cup cools gradually. A radiator warms a room. Sunlight raises the temperature of a stone 1 quiet degree at a time. Yet beneath this smooth experience, thermal behavior emerges from enormous numbers of microscopic particles exchanging energy according to quantum rules. Temperature is not simply a measure of how much energy an object contains. It describes the statistical distribution of energy among the microscopic degrees of freedom available to the particles within a system. A degree of freedom is a way in which energy can be stored. A gas molecule may move through space in 3 directions. It may rotate. Its atoms may vibrate relative to one another. Its electrons may occupy higher energy states. Different substances offer different combinations of these possibilities, and temperature helps describe how the available energy is shared among them. This is distinct from internal energy. Internal energy is the total microscopic energy contained within a system. It includes the kinetic energy associated with particle motion, the potential energy of interactions, molecular vibration, rotation, electronic states, and other microscopic contributions. 2 objects can have the same temperature while containing very different amounts of internal energy. A warm swimming pool contains far more total internal energy than a cup of water at the same temperature, because it contains vastly more matter. Heat is different again. Heat is energy transferred from one system to another because of a temperature difference. It is not a material substance stored inside an object. Once the transfer has occurred, the energy becomes part of the receiving system's internal energy. A hot cup does not contain a special fluid called heat. It contains internal energy. When it warms the surrounding air, energy is transferred as heat. This distinction may sound a little particular, but thermodynamics is rather fond of being particular. It saves confusion later. Atoms and molecules can store energy in several ways. In gases, particles move through space, giving them translational kinetic energy. Molecules may also rotate and vibrate. At sufficiently high temperatures, electrons can be promoted into excited states, adding electronic energy. Not every form of motion is equally accessible at every temperature. A simple monatomic gas, made of individual atoms, stores most of its thermal energy in translational motion under ordinary conditions. A molecule made of two or more atoms can also rotate. Its atoms can vibrate around their equilibrium positions, although these vibrational modes may require more energy to excite. Quantum physics determines which energy values are allowed. Molecular rotations possess discrete rotational energy levels. Vibrations are also quantized. A molecule cannot vibrate with just any arbitrary energy. It can occupy particular vibrational states separated by finite energy gaps. At low temperatures, thermal motion may not provide enough energy to reach the higher states. Those degrees of freedom effectively remain frozen out. This idea becomes especially important in solids. The atoms in a crystal are arranged in an organized lattice. They are not perfectly motionless. Each atom vibrates around an equilibrium position while interacting with its neighbors. Because the atoms are connected through electromagnetic forces, their vibrations are collective. A disturbance in one region influences nearby atoms, producing waves of motion through the lattice. Quantum mechanics describes the energy of these collective vibrations in discrete units called phonons. A phonon is not a tiny solid object moving between atoms like a marble passed down a row. It is a quantist excitation of a collective vibrational mode. The entire lattice participates in the motion, just as many sections of a string participate in a standing wave. The phonon is a convenient and physically meaningful way to describe how the vibrational energy is quantized. In many non-metallic solids, phonons carry much of the thermal energy. A hot region contains a greater population of energetic lattice vibrations. Through interactions among phonons, crystal imperfections, and boundaries, this energy spreads toward cooler regions. The ease with which phonons move through a material helps determine its thermal conductivity. A well-ordered crystal may allow some vibrational modes to travel relatively far before scattering. Defects, impurities, and irregular boundaries interrupt them. This is one reason the microscopic structure of a material strongly affects how efficiently it conducts heat. Phonons also contribute to heat capacity. Heat capacity measures how much energy must be added to raise the temperature of a system by a particular amount. If many microscopic energy states are available, the system can absorb substantial energy across those states. Classical physics attempted to describe this sharing through the equipartition theorem. In suitable high-temperature conditions, equipartition assigns an average amount of thermal energy to each independent quadratic degree of freedom. This produces useful predictions for gases and some solids. For a classical solid, each atom contributes through kinetic and potential vibrational energy. The resulting prediction suggests a roughly constant heat capacity at sufficiently high temperatures. This works surprisingly well in that regime. At lower temperatures, however, experiments show that the heat capacities of solids decrease. Classical equipartition cannot explain why. It assumes energy can be distributed continuously among every vibrational mode, even when the available thermal energy is very small. Quantum mechanics provides the missing restriction. A vibrational mode can absorb energy only in quanta. High-frequency modes require relatively large quanta and may remain inaccessible when the temperature is low. If thermal energy is insufficient to excite a mode, that mode contributes little to the heat capacity. As the material cools, fewer vibrational states remain accessible. Albert Einstein developed an early quantum model of solid heat capacity in 1907. He treated the atoms as quantum oscillators sharing one characteristic frequency. Einstein's model correctly predicted that heat capacity should fall at low temperature. It demonstrated that quantization could explain a failure of classical thermal physics, much as Max Planck's work had done for blackbody radiation. The model was not fully accurate at the coldest temperatures because real crystals support many vibrational frequencies rather than only one. Peter Debye improved the theory by treating the lattice as a continuous elastic medium with a range of vibrational modes up to a maximum frequency. The Debye model correctly predicts that, at very low temperatures, the heat capacity of many crystalline solids decreases approximately with the third power of temperature. The falling heat capacity is therefore a direct sign that energy modes are being frozen out. The particles and excitations carrying thermal energy also follow quantum statistics. Satyendra Nath Bose developed a new method of counting quantum states while studying photons. Albert Einstein extended the idea to material particles. The resulting framework became known as Bose-Einstein statistics. Bosons are particles or excitations with integer spin. They do not obey the Pauli exclusion principle. Many identical bosons can occupy the same quantum state. Photons are bosons. Phonons are bosonic excitations. Their populations follow Bose-Einstein statistics, which strongly influences the way thermal energy is distributed among radiation and lattice vibrations. Fermions behave differently. Electrons, protons and neutrons have half-integer spin and follow Fermi-Dirac statistics. The Pauli exclusion principle prevents identical fermions from occupying the same quantum state. At low temperatures, electrons in a metal cannot all drop into the single lowest energy state. They fill available states up to the Fermi energy. Only electrons near the highest occupied energies can easily change states and participate in many thermal processes. This is why the electronic contribution to heat capacity differs from a simple classical prediction. Quantum identity changes thermal behavior. Bosons can gather into shared states. Fermions must spread across available states. Phonons appear and disappear as vibrational energy changes. Electrons rearrange only where exclusion leaves room. Yet the macroscopic result feels smooth. Temperature, heat capacity, thermal conductivity, and the flow of heat emerge from unimaginably large numbers of quantum events. No single phonon has a temperature. No individual electron carries the full thermal state of a metal. Thermodynamics appears when the statistical behavior of the entire system becomes stable and predictable. At ordinary temperatures, quantum energy exchanges blend into the familiar warmth of matter. At very low temperatures, however, accessible states become scarce. Thermal motion fades, and collective quantum behavior becomes increasingly visible. Cooling matter does not simply make everything move more slowly. It gradually removes entire pathways through which energy can be stored. Near the lowest temperatures nature allows, the distinction between microscopic quantum rules and macroscopic behavior begins to blur. Every quantum system has a lowest allowed energy. This minimum energy condition is called the ground state. The ground state does not necessarily mean that every part of the system has stopped moving, nor does it mean that all measurable activity has vanished. It simply means that the system occupies the lowest energy state permitted by its physical structure and by the rules of quantum mechanics. A useful example is the quantum harmonic oscillator. A harmonic oscillator is any system in which a restoring force pushes an object back toward an equilibrium position. A mass attached to a spring is the familiar classical example. Move the mass away from the center and the spring pulls it back. The mass overshoots, reverses direction, and continues to oscillate. In classical physics, the oscillator can gradually lose energy until it rests perfectly at equilibrium. Its position can be exactly fixed, its momentum can be exactly zero, and its total energy can fall all the way to zero. The quantum version behaves differently. The allowed energies of a quantum harmonic oscillator form a series of discrete levels. Even in its ground state, the oscillator retains a small but non-zero amount of energy. This minimum is called zero-point energy. The ground state energy can be stated in spoken form. The lowest energy of a quantum harmonic oscillator equals 1/2 of Planck's constant divided by 2π, multiplied by the oscillator's angular frequency. The expression is often written using the reduced Planck constant, but its physical meaning is more important than the notation. The minimum energy depends on the oscillator's natural frequency. A higher frequency oscillator has a larger ground state energy. Why can the energy not fall to zero? The uncertainty principle provides the answer. If the oscillator rested exactly at its equilibrium position, then its position would be perfectly known. If it also had exactly zero momentum, its momentum would be perfectly known as well. Quantum mechanics does not allow both quantities to be fixed with unlimited precision. A perfectly localized oscillator must possess a spread of possible momenta. A state with exactly zero momentum must be spread across position. The lowest energy state balances these competing requirements. The oscillator's position remains distributed around the equilibrium point, and its momentum also has a range of possible values. This produces a non-zero average kinetic energy and a non-zero average potential energy. The system is as quiet as quantum mechanics allows, but not completely motionless. The phrase zero-point motion is sometimes used to describe this remaining ground state behavior. It should not be imagined as an ordinary particle following one hidden path and physically trembling at one definite speed. The quantum state instead contains probability distributions for position and momentum. Zero-point energy remains even at absolute zero. Absolute zero is the lowest limit of the thermodynamic temperature scale. It corresponds to 0 Kelvin, or approximately minus 273.15 degrees Celsius. Cooling a system toward absolute zero removes thermal excitations. Particles lose access to many higher energy states, and the system approaches its ground state. Absolute zero does not mean that every atom becomes perfectly still. It does not erase quantum uncertainty, zero-point motion, or the ground state activity of fields. It is also not generally possible to reach absolute zero through a finite sequence of ordinary cooling operations. The third law of thermodynamics implies that the closer a system comes to 0 Kelvin, the more difficult further cooling becomes. Researchers have nevertheless produced temperatures extraordinarily close to it. At such low temperatures, quantum behavior that is usually hidden by thermal motion can become visible across much larger scales. One of the clearest examples is the Bose-Einstein condensate. Bosonic particles do not obey the Pauli exclusion principle. Many identical bosons can occupy the same quantum state. At ordinary temperatures, their thermal motion spreads them across many different states. As a dilute gas of bosonic atoms is cooled, their de Broglie wavelengths become longer. Eventually, those wavelengths overlap. A large fraction of the atoms then enters the same lowest energy quantum state. The result is a Bose-Einstein condensate. The possibility was predicted through the work of Satyendra Nath Bose and Albert Einstein during the 1920s. It remained experimentally unreachable for many decades because the required temperatures were so low. In 1995, Eric Cornell and Carl Wieman produced a Bose-Einstein condensate, using rubidium atoms cooled to a tiny fraction of a degree above absolute zero. Wolfgang Kettel soon created condensates containing larger numbers of sodium atoms and developed methods for studying their coherent behavior. Eric Cornell, Carl Wieman, and Wolfgang Kettel later shared the Nobel Prize in Physics for 2001. Inside a condensate, the atoms do not disappear into one physical object. They remain atoms, but many are described by a shared macroscopic quantum state. Their behavior can display interference, coherence, quantist vortices, and collective motion usually associated with much smaller quantum systems. The wave-like properties of matter become visible across distances far greater than the size of an individual atom. Another related phenomenon is superfluidity. Superfluid helium can flow with extraordinarily low resistance. It may pass through extremely narrow openings, climb the walls of containers in thin films, and sustain persistent circulation. Superfluidity was discovered in liquid helium during the late 1930s through experiments by Piotr Kapitsa, and independently John Allen and Don Misner. Helium-4 atoms are bosons, and below a temperature of roughly 2.17 Kelvin, liquid helium enters a superfluid phase. The transition is associated with large-scale quantum coherence, although the strongly interacting liquid is more complicated than an ideal dilute Bose-Einstein condensate. A superfluid does not behave like an ordinary liquid that has merely become very cold. Its motion is constrained by collective quantum states. Circulation can become quantized. Vortices appear with specific allowed amounts of rotational motion. Heat can propagate through the liquid in unusual wave-like patterns known as second sound. These phenomena reveal what happens when thermal disorder becomes weak enough for quantum organization to dominate. The ground state is therefore not an empty absence of behavior. It can possess structure, correlations, motion, and collective properties. This sometimes leads to claims that zero-point energy could provide an unlimited source of power. The idea sounds attractive. If every quantum system retains energy in its ground state, perhaps that energy could simply be extracted and used. The difficulty is that the ground state is already the lowest energy configuration available. To extract useful energy from a system, it must move into a state of lower energy, while transferring the difference elsewhere. A system already in its true ground state has nowhere lower to go. Zero-point energy can influence measurable effects, and changes in boundary conditions can alter differences between ground state energies. But this does not create an unrestricted supply of energy from nothing. A machine cannot repeatedly drain a ground state and leave it somehow below its own minimum. Nature has already placed the floor there, and it is not known for offering basement extensions. The same idea becomes broader in quantum field theory. Each mode of a quantum field behaves mathematically like a quantum oscillator. Every mode has a ground state, and those ground states contribute to the structure of the quantum vacuum. The vacuum is therefore not simply empty space with all physical content removed. It is the lowest energy state of the quantum fields that extend throughout space. Just as a cooled oscillator retains zero-point energy, quantum fields retain ground state fluctuations and correlations even when no ordinary particles are present. The lowest energy nature allows is not always zero in the classical sense. It is the minimum compatible with quantum uncertainty, field structure, and the available states of the system. At ordinary temperatures, that minimum is buried beneath thermal motion. Near absolute zero, it begins to reveal itself through condensates, superfluids, and collective quantum behavior. And when the same principle is applied not merely to atoms or oscillators, but to the fields filling all of space, the ground state becomes the quantum vacuum itself. Quantum mechanics describes atoms, electrons, photons, and other microscopic systems with extraordinary precision. Special relativity describes how space, time, energy, and momentum behave when objects move close to the speed of light. To describe particles that can be created, destroyed, and transformed while still respecting both frameworks, physicists developed quantum field theory. Quantum field theory changes the basic picture of what a particle is. Instead of treating the universe as an empty stage containing separate little objects, the theory describes fundamental fields extending throughout space. There is an electron field, a quark field, an electromagnetic field, and other quantum fields associated with the known particles and interactions. These fields are present everywhere, even in regions where no ordinary particles are detected. A particle is understood as a quantist excitation of its corresponding field. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. This does not mean that a particle is merely an ordinary ripple in a classical medium. Quantum fields are mathematical and physical entities governed by quantum rules. Their excitations can carry energy, momentum, spin, electric charge, and other measurable properties. The development of this framework required many stages. Paul Dirac created a relativistic quantum equation for the electron in 1928. His theory successfully combined important features of quantum mechanics and special relativity, while also predicting the existence of antimatter. Later, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed powerful formulations of quantum electrodynamics. Quantum electrodynamics describes interactions between electrically charged particles and the electromagnetic field. Its predictions are among the most accurate ever tested in science. The theory explains phenomena ranging from the scattering of electrons and photons to tiny corrections in atomic energy levels and the magnetic properties of particles. Energy remains central throughout this description. A quantum field can be separated mathematically into many possible modes. Each mode behaves somewhat like a quantum harmonic oscillator. It has a collection of allowed excitation energies in the lowest possible state. Adding one quantum of excitation to a particular mode creates what may be observed as a particle with a corresponding energy and momentum. Removing that excitation returns the field mode toward a lower energy state. Even when no ordinary particles are present, the fields do not simply disappear. They remain in their lowest available configuration. This lowest energy state is called the quantum vacuum. The quantum vacuum is not the same as absolute nothingness. It is not a region from which all physical structure has been removed. It is the ground state of the interacting quantum fields. A vacuum can contain no detectable electrons, photons, or other ordinary particles while still possessing field correlations and ground state properties. The word empty therefore becomes rather delicate. A room may be empty of furniture. Interplanetary space may contain very little matter. A laboratory vacuum may contain far fewer gas molecules than the surrounding atmosphere. The quantum vacuum is a more precise concept. It refers to the lowest energy state permitted by the relevant field theory. Vacuum fluctuations are often described as particles continually appearing and disappearing from nothing. That image is memorable, but it can be misleading. The vacuum does not necessarily contain a swarm of ordinary particles briefly popping into measurable existence. Vacuum fluctuations refer more carefully to the statistical behavior, uncertainties, and correlations of quantum fields in their ground state. When particular measurements are performed, field quantities do not always return perfectly fixed values. Their possible outcomes have characteristic distributions, even in the vacuum state. These ground state properties influence real physical processes. One example is the Lamb shift. According to an early treatment of the hydrogen atom, two particular electron states should have exactly the same energy. In 1947, Willis Lamb and Robert Rutherford measured a small difference between them. The shift arises through the interaction between the electron and the quantized electromagnetic field. Vacuum fluctuations and radiative corrections alter the energies of the atomic states slightly. The effect is small but precisely measurable. Spontaneous emission is also connected with the quantum electromagnetic field. An excited atom can move to a lower energy state and emit a photon even when no external light is shining upon it. In quantum field theory, the atom interacts with the vacuum modes of the electromagnetic field. The vacuum is not supplying free energy. The emitted energy comes from the atom's transition to a lower state. The field provides the quantum framework through which that transition and photon emission occur. Vacuum polarization offers another example. In quantum electrodynamics, the presence of a charged particle affects the surrounding quantum fields. The vacuum responds in a way that slightly modifies the effective electromagnetic interaction. This produces measurable corrections in atomic physics and particle scattering. Again, it is tempting to picture short-lived particle pairs physically filling space. Feynman diagrams often contain internal electron and positron lines that make this picture feel natural. But those internal lines represent terms in a calculation, rather than directly observed particles following definite hidden paths. The Casimir effect is perhaps the most famous phenomenon associated with the quantum vacuum. Hendrik Casimir predicted in 1948 that two closely spaced, uncharged conducting plates could experience an attractive force. The plates alter the allowed electromagnetic field modes between them compared with those outside. The resulting difference in the field's ground state structure produces a measurable force. For ideal parallel plates, the force becomes stronger very rapidly as the separation decreases. At distances of only a few hundred nanometers, it can be detected with sensitive instruments. The Casimir effect is often described as direct proof that empty space contains an enormous store of energy. The reality is more careful. The measurable quantity is the difference between physical configurations. Quantum field theory is extremely successful at predicting such energy differences. The absolute energy associated with every field mode is more difficult, because there are modes of arbitrarily high frequency in the mathematical theory. A straightforward sum of their ground state energies produces an infinite result. Physicists handle these infinities through procedures known as regularization and renormalization. Regularization introduces a controlled mathematical method for organizing divergent expressions. Renormalization then connects the theoretical parameters with quantities defined by measurement, allowing finite and accurate predictions to emerge. This is not simply the casual deletion of inconvenient infinities. It is a systematic framework that has been tested through extraordinarily precise experiments. For most particle and atomic processes, only energy differences and changes affect the observable result. An arbitrary constant added to every energy value does not alter the dynamics of ordinary quantum mechanics. Gravity changes the situation. According to general relativity, energy contributes to the curvature of space-time. If the quantum vacuum possesses an absolute energy density, that energy should have gravitational effects. Observations of the accelerating expansion of the universe are commonly described using dark energy, or a cosmological constant. The associated energy density is extremely small by particle physics standards, yet it appears to influence the evolution of the entire cosmos. Simple estimates of quantum vacuum energy can exceed the observed cosmological value by an enormous number of orders of magnitude, depending on the assumptions and energy scale used. This mismatch is known as the cosmological constant problem. Quantum field theory explains interactions among particles with astonishing precision. General relativity explains gravity and the large-scale structure of space-time with equal success. Yet the meaning of vacuum energy, where these theories meet, remains unresolved. Empty space is therefore not truly empty in the quantum description. It contains fields in their lowest energy states, along with measurable correlations and subtle effects. But whether that ground state energy curves the universe in the way straightforward reasoning suggests remains one of the deepest unanswered questions in modern physics. Albert Einstein's most famous relation changed the meaning of both mass and energy. Before relativity, mass was usually treated as a fixed measure of how much matter an object contained, while energy described motion, position, heat, or some other changeable property. Einstein showed that these ideas are not entirely separate. An object at rest still possesses energy simply because it has mass. The relation can be stated in spoken form. Rest energy equals mass multiplied by the speed of light multiplied by the speed of light. Because the speed of light is approximately 300 million meters per second, multiplying it by itself produces an enormous conversion factor. Even a very small amount of mass corresponds to a very large amount of rest energy. 1 gram of mass corresponds to roughly 90 trillion joules of rest energy. That does not mean a 1 gram object can casually release all of this energy. Most ordinary matter is stable, and there is usually no accessible process that converts its entire mass into other forms. The relation describes what the mass represents, not an invitation for every teaspoon to become alarmingly ambitious. Mass should not be imagined as a container filled with ordinary kinetic energy. It is better understood as a property of the total energy of a system when viewed in the system's own rest frame. For a single elementary particle, rest mass is one of its intrinsic measurable properties. An electron, for example, has a rest mass corresponding to a rest energy of about 511,000 electron volts. An electron is currently treated as elementary. No smaller internal parts have been detected within it. Its mass is connected to its interaction with the Higgs field. Composite particles are more complicated. A proton is built from quarks and gluons. Its simplest description contains 2 up quarks and 1 down quark, known as its valence quarks. Yet the proton is not merely 3 tiny objects sitting quietly inside a boundary. Its interior is an intensely dynamic quantum system, containing quark fields, gluon fields, and continually changing contributions from quark and antiquark excitations. The theory describing these interactions is quantum chromodynamics. Quantum chromodynamics is the quantum field theory of quarks, gluons, and the strong nuclear interaction. Quarks carry a property called color charge, while gluons transmit the strong interaction and also interact with one another, because they themselves carry color charge. The word color here has no connection with visible color. It is simply the name given to a type of quantum charge. The strong interaction confines quarks inside composite particles such as protons and neutrons. Isolated quarks have never been observed under ordinary conditions. The masses of the up and down quarks contribute only a small fraction of the proton's total mass. Most of the proton's mass comes from the energy of the quantum chromodynamic system itself. The quarks possess kinetic energy. The gluon fields carry energy. The interactions among the fields contribute further energy. In the proton's rest frame, the total of these contributions appears as the proton's mass. This is one of the clearest examples of mass emerging from confined quantum energy. The proton weighs far more than the simple sum of the rest masses of its 3 valence quarks. Most of the mass of familiar objects therefore comes not directly from the Higgs field, but from quantum chromodynamic energy inside protons and neutrons. The Higgs field remains essential, however. The Higgs field has a non-zero background value throughout empty space. Elementary particles that interact with this field acquire rest mass according to the strength of that interaction. Electrons interact relatively weakly with the Higgs field and have a small mass. The top quark interacts far more strongly and is much heavier. The mechanism was developed through the work of several physicists, including Peter Higgs, François Englert, and Robert Brute. A corresponding excitation of the Higgs field, known as the Higgs boson, was discovered in 2012 by the ATLAS and CMS collaborations at the European Organisation for Nuclear Research. The Higgs boson's discovery confirmed a crucial part of the standard model of particle physics, but the phrase, "the Higgs field gives everything mass," is too simple. The Higgs field contributes to the intrinsic masses of elementary particles such as electrons and quarks. It does not directly explain most of the mass of ordinary visible matter. That mass is dominated by the energy of the strong interaction inside atomic nuclei. Mass can also change when systems bind together. Consider several protons and neutrons combining to form an atomic nucleus. If the final bound nucleus has a lower total energy than the separated particles, energy is released during its formation. Because the bound system now has less total rest frame energy, it also has less mass. The difference is called the mass defect. This missing mass has not vanished. It has left the system as radiation, kinetic energy, or another form of released energy. The energy required to separate the nucleus back into its individual protons and neutrons is called the binding energy. A tightly bound nucleus has a substantial binding energy and therefore a lower mass than its separated components. This relationship drives nuclear processes. In nuclear fission, a heavy nucleus, such as uranium, splits into smaller nuclei. The products are more tightly bound overall, so their total mass is slightly lower than the mass of the original nucleus and any incoming particle. The mass difference appears as kinetic energy electromagnetic radiation, and the motion of emitted neutrons. In nuclear fusion, light nuclei combine into a more tightly bound nucleus. When hydrogen nuclei eventually form helium, the helium nucleus has less mass than the original particles taken separately. The difference is released as energy. This is the process powering the sun. Inside the solar core, hydrogen is gradually converted into helium through a chain of nuclear reactions. Approximately 4 hydrogen nuclei ultimately contribute to the formation of one helium nucleus, along with neutrinos and other reaction products. The final helium nucleus contains slightly less mass than the original hydrogen nuclei. Around 0.7% of the starting mass is converted into other forms of energy. That fraction sounds modest, but the sun processes an enormous amount of hydrogen. Every second, roughly 600 million tons of hydrogen are converted into helium. About 4 million tons of mass become radiation and kinetic energy during that same interval. The resulting energy moves outward through the sun and eventually reaches space as sunlight, while neutrinos escape directly from the nuclear reactions. Radioactive decay also reflects differences in rest energy. An unstable nucleus can transform into a lower energy arrangement while emitting particles or radiation. The combined rest masses and kinetic energies of the products must match the total energy of the original system. Particle-antiparticle annihilation provides an even more direct example. When an electron meets a positron under suitable conditions, their rest energy can be converted into photons. Momentum conservation usually requires at least 2 photons in the simplest annihilation process. The matter has not disappeared into nothing. Its rest energy has become electromagnetic energy. The reverse process is possible as well. A sufficiently energetic photon interacting near another particle can contribute to the creation of a particle, and its antiparticle, provided all conservation laws are satisfied. Energy can therefore become massive particles, and massive particles can become radiation. Mass and energy are not interchangeable labels for exactly the same thing in every circumstance. Mass is the invariant energy of a system in its rest frame, while energy also depends on motion and on the observer's frame of reference. The deeper connection is that the mass of any complete system reflects its total internal energy. A warm object has very slightly more mass than the same object when cold. A charged battery has slightly more mass than the same battery after its stored energy has been released. A bound nucleus has less mass than its separated particles because binding energy has left the system. These differences are normally far too small to notice with an ordinary scale, but the principle is universal. The mass of matter is therefore not merely something attached to particles from outside. It can arise from the energy of fields, motion, confinement, interactions, and binding. Inside every proton, quantum chromodynamic fields contribute most of the mass. Across empty space, the Higgs field contributes to the masses of elementary particles. Within nuclei, differences in binding energy determine which transformations can release power. Mass is one of the forms in which energy appears when a physical system is viewed at rest, and when quantum systems collide, decay, combine, or annihilate, that stored energy can be rearranged into new particles, new motion, and new radiation, always under the guidance of the same conservation laws. Quantum systems do not exchange energy at random. Every interaction is governed by the properties of the systems involved, the strength with which their fields couple, and the conservation laws that restrict which outcomes are possible. An atom can absorb light, emit light, collide with another particle, or decay into a different arrangement. In each case, energy is redistributed rather than created or destroyed. The simplest example is stimulated absorption. An atom in a lower energy state can absorb a photon if the photon carries the correct amount of energy. The photon disappears as a detectable excitation of the electromagnetic field, while the atom moves into a higher energy state. The relation remains precise. The energy of the absorbed photon equals the difference between the atom's initial and final energy levels. A photon with the wrong energy may pass by without causing that transition. Quantum systems are selective. They do not generally accept whatever energy happens to be nearby with the relaxed enthusiasm of someone approaching a buffet. An excited atom can return to a lower energy state through spontaneous emission. In this process, the atom emits a photon even when no external light is deliberately applied. The energy carried away by the photon equals the energy lost by the atom. The direction and exact moment of emission cannot usually be predicted for one individual atom. Quantum theory instead provides a probability that the decay will occur within a given period. A third process is stimulated emission. If a photon with the appropriate energy passes an atom that is already excited, the interaction can encourage the atom to move into a lower state and emit a second photon. The emitted photon matches the stimulating photon in frequency, phase, direction, and polarization under the idealized description. This ability to produce coherent copies of light is the foundation of the laser. Albert Einstein described absorption, spontaneous emission, and stimulated emission using a set of probability coefficients in 1917. His analysis showed how matter and radiation could remain in thermal equilibrium. Absorption moved atoms upward in energy, while spontaneous and stimulated emission moved them downward. Stimulated emission remained largely theoretical until physicists learned how to control large populations of excited atoms. Charles Townes helped develop the MESA, a device that produces coherent microwave radiation through stimulated emission. Arthur Schawlow and Charles Townes later described how the same principle could be extended to optical frequencies. In 1960, Theodore Myman built the first working laser using a synthetic ruby crystal. A laser requires a population inversion. This means more atoms or molecules must occupy a chosen excited state than the lower state involved in the desired transition. Energy is first supplied through pumping, perhaps using light, electricity, or another process. Photons produced by stimulated emission then pass through the active material, triggering further emissions. Mirrors around the material allow the light to travel back and forth, increasing amplification. A portion escapes as the laser beam. The device does not create energy from nothing. It converts energy supplied by the pump into highly organized electromagnetic radiation. Quantum interactions also transfer energy through collisions. When particles collide, their translational kinetic energy can be redistributed into new directions of motion. It may also become internal excitation, vibration, rotation, particle creation, or emitted radiation. A fast electron striking an atom may transfer enough energy to raise one of the atom's electrons into a higher state. A more energetic collision may remove the electron entirely, ionizing the atom. The excited or ionized system can later release energy through photons, further collisions, or recombination. Scattering experiments are controlled studies of these exchanges. Researchers send particles toward a target and measure the energies, directions, and identities of the products. From these results, they infer the structure of the target and the interaction responsible. Ernest Rutherford's scattering experiments revealed the atomic nucleus. Later, deep inelastic scattering experiments showed that protons contain smaller constituents identified as quarks. Modern scattering calculations often use Feynman diagrams. A Feynman diagram represents a mathematical term contributing to the probability of a quantum interaction. External lines correspond to particles prepared or detected in an experiment. Vertices represent couplings between fields. Internal lines represent propagators within the calculation. The diagram should not be read as a literal film of tiny particles travelling along visible paths. A photon drawn between two electron lines does not necessarily represent an ordinary detectable photon briefly flying through space. The diagram organizes mathematical contributions to the final prediction. Different diagrams may contribute to the same measurable outcome, and their quantum amplitudes must be combined before probabilities are calculated. energy and momentum remain conserved at every interaction vertex. The strength of an interaction depends partly on its coupling constant. A stronger coupling generally makes a process more likely, although the complete probability also depends on energy, momentum, available states, and quantum interference. Unstable particles and excited states transfer energy through decay. A decay occurs when a state can transform into a lower energy collection of products while obeying all relevant conservation laws. Total energy must be conserved. Total momentum must be conserved. Electric charge must remain balanced. Depending on the interaction, other quantities such as angular momentum, color charge, or lepton number also constrain the possible products. Beta decay once appeared to challenge this careful accounting. In one form of beta decay, a neutron inside a nucleus transforms into a proton while an electron is emitted. Early measurements showed that the electron did not always carry one fixed energy. Its energy varied across a continuous range. If only the recoiling nucleus and electron were produced, the missing energy seemed to have vanished. Wolfgang Pauli proposed a solution in 1930. He suggested that an unseen neutral particle was carrying away the missing energy and momentum. Enrico Fermi later developed a theory of beta decay and gave the particle the name neutrino. In modern terms, ordinary beta-minus decay can be described as a neutron transforming into a proton, an electron, and an electron antineutrino. The energy is shared among the products. The electron's value varies because the antineutrino and recoiling nucleus take different shares in different events. The neutrino was eventually detected experimentally, confirming that conservation had been preserved. Particle accelerators make these exchanges much more energetic. The Large Hadron Collider at the European Organization for Nuclear Research accelerates protons to energies of several trillion electron volts before bringing them into collision. Only part of each proton's energy is carried by the individual quarks or gluons that actually interact. Even so, the collisions can concentrate enough energy into a tiny region to produce heavy, short-lived excitations of quantum fields. Kinetic energy becomes rest energy. New particles appear, then rapidly decay into lighter products that detectors can measure. This is how the Higgs boson, top quarks, heavy weak bosons, and many other particles are studied. The accelerator does not manufacture matter from absolute nothingness. It rearranges the energy of motion into new field excitations while preserving every applicable conservation law. The same principles operate in quieter technologies. Lasers control stimulated emission. Light-emitting diodes guide electrons across semiconductor energy gaps. Solar cells use absorbed photons to create mobile charge carriers. Atomic clocks measure exceptionally stable transitions between quantum states. Human technology works by preparing systems, controlling their couplings and directing how energy is allowed to move. At the microscopic level, every transfer is shaped by discrete states, probability amplitudes, field interactions, and conservation laws. A photon is absorbed, an atom changes state, a particle scatters, an unstable excitation decays. The details vary, but the central pattern remains the same. Quantum interactions do not loosen the rules of energy. They reveal the precise mechanisms through which energy moves from one physical form into another. Quantum physics began as an attempt to understand a handful of stubborn experimental problems. Today, the same ideas quietly operate inside many of the technologies used every day. Lasers provide one of the clearest examples. A laser depends on atoms, molecules, or solid materials possessing distinct quantum energy levels. Energy is first supplied to the laser medium, raising particles into excited states. This process is called pumping. Under ordinary conditions, most particles occupy lower energy states. A functioning laser requires population inversion, in which more particles occupy a selected excited state than the lower state, involved in the desired transition. A passing photon can then stimulate an excited particle to release a second photon. The emitted photon matches the first in frequency, phase, direction, and polarization. Repeated stimulated emission produces coherent electromagnetic radiation. This coherence allows laser light to remain narrow, organized, and precisely controlled. Lasers now read optical discs, carry information through fiber optic cables, scan barcodes, cut industrial materials, perform surgery, measure distances, and cool atoms to extremely low temperatures. Magnetic resonance imaging also depends on quantum energy states. Atomic nuclei possess a quantum property called spin. Nuclei with suitable spin behave as tiny magnetic systems when placed inside an external magnetic field. The field separates their possible spin states into slightly different energies. Isidore Rabi developed methods for studying transitions between such quantum states using oscillating electromagnetic fields. Felix Bloch and Edward Purcell later demonstrated nuclear magnetic resonance in condensed matter. Magnetic resonance imaging applies these principles mainly to hydrogen nuclei within the body. A strong magnetic field creates an energy difference between nuclear spin states. Radio frequency pulses then drive transitions between them. As the nuclei return toward equilibrium, they produce signals that vary with the surrounding tissue. Magnetic field gradients encode position, allowing computers to reconstruct detailed images of internal anatomy. The technique does not illuminate the body with ordinary visible light. It listens to carefully controlled quantum transitions in atomic nuclei. Atomic clocks use an even more precise form of energy measurement. Atoms of the same isotope possess identical internal energy structures. A transition between two selected states therefore has an exceptionally stable frequency. Cesium atomic clocks use the microwave frequency associated with a transition between two hyperfine states of cesium-133 atoms. The second is defined using exactly 9,192,631,770 periods of the radiation associated with that transition. Atomic clocks are essential to satellite navigation. A timing error of only 1/1,000,000th of a second would correspond to a distance error of roughly 300 meters for a signal traveling at the speed of light. Navigation satellites therefore carry highly precise clocks, while their systems also include corrections predicted by special relativity and general relativity. Atomic timing supports telecommunications, electrical networks, financial systems, astronomical observations, and fundamental tests of physics. Laboratories such as the National Institute of Standards and Technology develop clocks so precise that differences in gravitational potential across small height changes can affect their measured rates. Semiconductor technology provides another vast application of quantum energy. Transistors work because electron motion can be controlled through energy bands, band gaps, electric fields, and carefully introduced impurities. Integrated circuits combine enormous numbers of these devices into processors and memory systems. Digital cameras use semiconductor sensors that absorb photons and convert their energy into electrical signals. Solar cells use similar transitions to convert sunlight into usable current. Light-emitting diodes perform the reverse process, releasing photons when electrons move between energy states. Quantum dots extend this control to extremely small structures. A quantum dot is a nanoscale region that confines electrons in all three spatial dimensions. Because the available space is so limited, the electron energy levels become discrete in a way resembling those of an artificial atom. The size of the quantum dot affects the spacing of its energy levels. Smaller dots generally emit higher energy, shorter wavelength light, while larger dots emit lower energy, longer wavelength light. This allows their color to be adjusted by changing their size rather than their basic chemical composition. Quantum dots are used in displays, imaging research, sensors, and experimental solar technologies. Quantum computing attempts to control energy states with still greater delicacy. Some quantum computers use superconducting circuits cooled to extremely low temperatures. These circuits are engineered to possess distinct quantum energy levels that can represent quantum bits. Other approaches use trapped ions. Individual electrically charged atoms are held by electromagnetic fields, while lasers manipulate transitions between carefully chosen internal states. Quantum information can be stored in superpositions and shared through entanglement. The challenge is preserving those fragile states long enough to perform useful operations before interactions with the environment cause decoherence. Major university laboratories, the National Institute of Standards and Technology, and research centres around the world study these systems. The European Organisation for Nuclear Research develops different but equally precise technologies for controlling particle beams, superconducting magnets, detectors, and high-energy collisions. None of these devices draws power from a vague substance called quantum energy. They depend on specific measurable effects, discrete transitions, electromagnetic coupling, spin, tunneling, interference, superconductivity, and the controlled movement of excitations through fields and materials. Quantum theory became technologically powerful because its predictions are precise enough to engineer. A photon promotes an electron across a semiconductor gap. A nucleus changes spin state inside a magnetic field. An atom measures time through a stable transition. A superconducting circuit preserves a delicate superposition. These are carefully organized versions of processes already occurring throughout nature. The same quantum rules that produce a laser beam also govern the light emitted by atoms in distant stars. The tunneling used in electronic devices helps nuclear reactions occur inside stellar cores. The energy levels measured by atomic clocks are part of the same microscopic structure that gives matter its stability. Human technology controls quantum energy across tiny laboratories and devices. Beyond them, the universe applies the same rules on a far greater scale, powering stars, creating elements, and shaping the radiation that travels across the cosmos. Quantum physics explains energy by describing the states a physical system is allowed to occupy, the way those states evolve through time, and the interactions through which energy passes between matter and fields. Energy itself remains a conserved physical quantity. It is not a material substance hidden inside particles, atoms, or empty space. Quantum theory does not replace ordinary energy with something more mysterious. It changes the rules governing which energy values are possible, how those values are measured, and how energy can be transferred. The first great clue came from blackbody radiation. Max Planck found that the measured spectrum of thermal light could be explained only if microscopic oscillators exchanged energy in discrete amounts. His energy quanta prevented classical theory from assigning unlimited energy to high-frequency radiation. Albert Einstein pushed the idea further. His explanation of the photoelectric effect showed that light transfers energy in localized quanta, whose energies depend on frequency. Brighter light supplies more photons, while higher frequency light supplies more energy in each photon. Wave mechanics then revealed why atoms possess distinct energy levels. The Schrödinger equation describes quantum states through wave functions. When a particle is confined by forces and boundary conditions, only certain stable wave patterns satisfy the equation. Each permitted state is associated with a particular energy. This quantized structure explains why atoms absorb and emit only selected wavelengths of light. It also explains why electrons remain in stable states rather than collapsing into atomic nuclei. Those atomic states shape the chemical world. Electron energy levels and the Pauli exclusion principle organize the periodic table. Chemical bonds form when combined arrangements of electrons and nuclei have lower total energy than separated atoms. Molecules possess quantized electronic, vibrational, and rotational states, producing characteristic spectra. When many atoms form a solid, their closely spaced energy levels develop into bands. The occupation of those bands determines whether a material behaves as a conductor, semiconductor, or insulator. Transistors, solar cells, digital cameras, and light-emitting diodes all depend on controlling electron transitions between these states. Heat also has a quantum foundation. In solids, collective lattice vibrations carry energy in quantized excitations called phonons. The availability of these vibrational states determines heat capacity and thermal conductivity, especially at low temperatures. Quantum fields extend the same principle still further. Particles are described as quantized excitations of underlying fields. Electrons arise from the electron field, photons from the electromagnetic field, and quarks from quark fields. Even the vacuum is not the absence of every physical property. It is the lowest energy state of the quantum fields, with measurable correlations and effects. Mass also reflects quantum energy. Elementary particles acquire intrinsic masses, partly through interactions with the Higgs field. Most of the mass of protons and neutrons, however, comes from the energy of quarks and gluons interacting through quantum chromodynamics. Nuclear binding energy explains why a bound nucleus has slightly less mass than its separated components. That difference can appear as radiation and kinetic energy during fusion, fission, or radioactive decay. None of this means that every kind of energy is divided into identical universal packets. A photon's energy depends on its frequency. Atomic transitions depend on the structure of the atom. Molecular vibrations, rotational states, particles in confined regions, and oscillations of fields all possess different energy spectra. Some systems have evenly spaced energy levels, many do not. Quantization depends on the physical system, the forces acting within it, and the boundary conditions imposed upon its wave function or field modes. Nature does not issue one standard parcel of energy and use it everywhere. Quantum measurement adds another layer. A system may occupy a state with one definite energy, or it may exist in a superposition containing several possible energy outcomes. Measuring the energy then produces one of those allowed values with a probability determined by the quantum state. This uncertainty does not mean the theory lacks precision. Quantum mechanics predicts the probability distribution and its evolution with extraordinary accuracy. A probabilistic measurement outcome can exist alongside exact conservation laws. When an atom emits a photon, the atom loses the same amount of energy gained by the electromagnetic field. When particles collide, their total incoming energy and momentum match the total carried by the products. The uncertainty lies in which a loud event occurs, not in whether nature remembers to balance the account. Yet important questions remain unanswered. The standard model of particle physics provides an exceptionally successful quantum description of known particles and three of the fundamental interactions. General relativity provides an equally successful description of gravity as the curvature of space-time. The two frameworks have not yet been united into a complete theory of quantum gravity. Energy becomes especially subtle where quantum fields and gravity meet. In general relativity, local energy and momentum remain conserved, but defining one total energy for the entire expanding universe is not always straightforward. Vacuum energy creates an even greater difficulty. Straightforward quantum field calculations suggest enormous contributions to the energy of empty space. Cosmic observations indicate that the effective energy associated with accelerated expansion is extraordinarily small by comparison. This mismatch is known as the cosmological constant problem. Depending on the assumptions used, the disagreement can reach many dozens or even more than 100 orders of magnitude. Dark energy describes the unknown cause of the observed accelerated expansion, but its underlying nature remains uncertain. It may involve a cosmological constant, a changing field, or physics not yet understood. Quantum physics has therefore explained an extraordinary amount about energy, without explaining everything. It tells us why atoms are stable, why light arrives in quantist exchanges, how chemical bonds form, why solids conduct electricity, how heat is stored, and how mass can emerge from fields and interactions. It does not turn energy into something vague or magical. Quite the opposite. Quantum physics makes the microscopic rules of energy more precise, more testable, and more surprising than classical intuition alone would ever suggest. Energy connects motion, matter, radiation, heat, mass, and space-time. Quantum theory reveals the hidden structure beneath those familiar forms, while leaving a few of the largest questions in the universe quietly open. Quantum physics explains energy by revealing the allowed states that physical systems can occupy, the probabilities associated with different measurement outcomes, and the precise rules through which energy moves between matter and fields. Classical mechanics and thermodynamics first showed that energy could be stored, transferred, and transformed while remaining conserved. Yet the blackbody radiation problem exposed a limit in that classical picture. Max Planck resolved it by proposing that microscopic systems exchange energy in discrete amounts. Albert Einstein carried the idea further through his explanation of the photoelectric effect. Light, he argued, transfers energy in photons, with each photon carrying an amount determined by its frequency. Atomic spectra then revealed that matter also possesses discrete energy structures. The Schrödinger equation described those structures through wave functions, while the Hamiltonian represented the total energy governing how quantum states evolve. A system could possess one definite energy, or exist in a superposition containing several possible outcomes. Despite this probability, energy conservation remains fundamental. Emmy Noether's theorem connects conservation with time translation symmetry, showing that when the laws governing an isolated system remain unchanged through time, energy is conserved. These quantum rules create the structure of atoms, the organization of the periodic table, chemical bonding, semiconductor energy bands, lasers, thermal behavior, and much of modern electronic technology. Even the lowest energy state retains quantum structure. Zero-point energy and the quantum vacuum produce measurable effects, but they do not offer an unlimited source of extractable power. A true ground state has no lower state into which it can repeatedly fall. Mass also reflects energy. Mass-energy equivalence connects rest mass with stored energy, while quantum chromodynamics explains why most ordinary mass comes from the energy of quarks and gluons inside protons and neutrons. Nuclear binding energy, the Higgs field, fusion, fission, and particle interactions complete different parts of the same picture. Quantum tunneling allows fusion to occur inside stars, while quantum field theory describes particles as excitations of fields extending through space and curved space-time. Important mysteries remain. Quantum gravity is incomplete. Vacuum energy and dark energy are not fully understood. The relationship between quantum fields and the expanding universe continues to challenge physics. Energy is familiar through motion, warmth, light, matter, and change. Yet beneath those familiar effects lies a deeper structure, conserved across every transformation, expressed through particles and fields, and governed at the smallest scales by the precise and often surprising rules of quantum physics.